Hello viewers, I'm Kausalya. Today we are going to solve problem 19. The problem is consider the system with the state equation, right? We are having x1 dot, x2 dot, x3 dot and as well as the respective output matrix y. Estimate the state controllability and observability by Gilbert's test, right? So here regarding this Gilbert's test, the first step is to calculate the eigenvalues. Okay, from the eigenvalues then we will proceed according to the steps which we need. So the first thing is to find eigenvalues. So from the given problem, right, this is your matrix A. So this is your A matrix, right? So here the characteristic equation is given by determinant of lambda I minus A, which is equal to 0. So here lambda I minus A is given by lambda and identity matrix, right? Since here we are having a 3 by 3 matrix, the identity matrix should be also of the same order, minus A. This is your given matrix A, right? So when you subtract these two matrices, what happens? This is your final output matrix, right? Lambda minus 0 gives you lambda. And here 0 minus 0 is 0 and again 0 minus 1 is minus 1, right? Similarly, you just proceed and finally calculate the matrix. The next step is we need to calculate the determinant of lambda I minus A, right? So as usual, here when you take lambda, you have to neglect this column and this row. So lambda plus 3 into lambda plus 3 minus 0 into minus 2, right? So lambda into lambda plus 3 whole square and here plus 0. So this term and this term, anyway it is 0, right? So leave it with 0 and here minus 1. So when you consider minus 1, 2 into minus 2 gives you minus 4, right? Now the next step is here we are expanding using the formula a plus b whole square, right? A square plus b square plus 2ab. Finally, when you solve, we are having an expression like this. So now we are solving this cubic expression by using trial and error method, right? So here we are assuming ourselves, let us give the value of this lambda as minus 1. Okay, it is random, you can substitute any values, right? But initially start with the minor values. Okay, if you give the value of lambda as 1, okay, anyways it is won't going to be give you the answer 0. That is 1 plus 6 plus 9 plus 4. It won't be equal to 0, right? So the next step we are proceeding with minus 1. So by this trial and error, you see, therefore this is what to say. The first thing is we have to substitute the value of 0 here. So 1 plus 0 is again 1, right? So 1 into minus 1 is minus 1. So 6 minus 1, 5. Minus 1 into 5 is minus 5. So 9 minus 5, 4. 4 into minus 1, minus 4. So 4 minus 4 is 0, right? Therefore, we are rewriting this cubic expression as one of the root is lambda plus 1, another root is lambda square plus 5 lambda plus 4, right? Only if we have lambda plus 1, that is, you see, lambda plus 1 is equal to 0. Then only we will be having lambda equal to minus 1, right? So, when you have minus 1, here you have to write it as plus 1. Right, again when you simplify this quadratic equation, the roots are lambda plus 1 and lambda plus 4. Therefore, when you solve this equation, finally the value of lambda are minus 1, minus 1, minus 4. So here we are giving specific names. Lambda 1 equal to minus 1, lambda 2 equal to minus 1 and lambda 3 equal to minus 4. Right. The next step is to find the eigenvectors. So how to find the eigenvectors? Again here the formula is lambda 1 I minus A, right? So lambda 1 again identity matrix minus A matrix. So when you solve this matrix, we are having the matrix, that is the final output matrix is like this, right? Now here we need to calculate the cofactors, right? Cofactors are calculated along the first row of the matrix. So this is your first row, right? So for this, we are calculating the cofactors. So how to calculate the cofactors? You see, we are naming cofactors as C11, C12 and C13. So how to calculate C11? You see, you have to leave this column and this row. So this you have to take determinant of these terms, right? So here that gives you C11, right? The next thing is C12. So C12 again, here the thing is you have to leave this row, right? This row and this column. So the remaining terms will be 2 into lambda 1 plus 3 and 0, 0, right? Never consider this term as 0, right? For considering cofactors, just you have to, for this term, what is the cofactor? That is the thing you should keep it in your mind, right? So, and again, here we are having this term, and finally for C13, that is, this is your C13. So, you have to leave this row and this column. So, these are the remaining terms over here, right? So, while writing expression, you see here, this is the normal rule, plus, minus, plus. Okay, these are all the signs you should include. So that is why here we are having a plus 1 and here minus 1 and here again plus 1, right? So when you solve, finally you are ending up with the expression like this, right? So here we had calculated C11, C12 and C13. The next step is we are going to calculate M1, M2 and M3, right? So M1 is nothing but C11, C12, C13. Just now we had calculated, right? So just write it over here. And the next thing is the value of lambda 1 is minus 1, right? When you substitute the value of lambda 1 as minus 1, you see, finally we are ending up with this matrix, right? And the next step is consider M2. M2 is nothing but differentiation of these cofactors, right? Again, when you differentiate this expression, you see lambda 1 square becomes 2 lambda 1 and here 6 lambda 1 becomes plus 6. And here minus 2 lambda 1 becomes minus 2 and 6 becomes 0. And here it is a constant. Whenever a constant is differentiated, the answer is 0, right? So the next thing is, again when you substitute the value of lambda 1 as minus 1, what happens? 2 into minus 1 becomes minus 2 plus 6. Once you solve, we are getting a matrix like this, right? And the next thing is, we are moving to the next step, that is lambda 3i minus a, right? Here you may have a question, why we have not included lambda 2i minus a? Can you guess the reason? Because lambda 1, lambda 2 holds the same value as minus 1, right? That is the reason we didn't calculate lambda 2i minus a. So we are switching to lambda 3i minus a here. So just when you substitute the values, lambda 3 is minus 4 and this is I and this is a, as usual we are having matrix. And again you have to find the cofactors along this first row. So when you find the cofactors, accordingly you see, again the same thing, here you have to consider plus and here minus and here plus, right? So just calculate the values and write it in the form of a matrix, and this is your M3, right? The next step is to find the canonical form of state model. So here the modal matrix M is given by M1, M2, M3. We know the values of M1, M2, M3, right? Just substitute it accordingly. Then the next thing is we have to calculate M inverse, right? So this is a quite big procedure, okay? But anyways, when you gradually solve problems, it will be familiar to you. So here M inverse is cofactor of M transpose divided by determinant of M. We know how to calculate the determinant of M, right? So here it is calculated, you see. So determinant of M value is minus 72. So now we are going to calculate cofactor of M and we have to find the transpose of it, right? So that is given as M cofactor transpose divided by del M. So del M is determinant, we have calculated, and next thing is we have to find cofactor for each and every term, right? Here totally we are having 9 terms, right? So we have to calculate 9 cofactors accordingly. So here you see cofactor of 4, okay? I had taken this first element. So when I take cofactor, what are all the values? minus 2, 2, 0 and minus 4, right? When you take again cofactor of this 4, what happens? We have to leave this column and this row. So minus 4, 2, minus 4, 4, right? When you consider this 1, what are all the elements? 4, minus 2, minus 4 and 0. So likewise, again when you consider this minus 4, you have to leave this row and this column. So the remaining terms are 4, 1, 0, minus 4, right? Accordingly, you have to calculate the cofactors for all these 9 terms, right? So again, calculating cofactors for the last row, minus 4, 0 and minus 4, right? So again, arrange them in the form of a matrix here accordingly. Next thing is we have to take transpose. Transpose is nothing but we have to convert rows into columns, right? And the next thing is calculating M inverse, right? We had calculated M cofactor transpose and we had already calculated the determinant of M. So determinant of M is minus 72 and this is your cofactor transpose matrix. So here in this case, we are just gradually reducing the numbers, that is we are dividing, right? So 8 by minus 72 can be written as minus 2 by 18, right? We are taking the common factor as 18 here. So we are dividing these numbers accordingly, right? The denominator term should be, you should have 18, right? So here we had find out the value of M inverse. I'll tell you the reason why we are ending up with this 18, okay? Then the next step is we have to calculate J. It is given by M inverse A and M, right? So M inverse is this matrix, A is given in the problem and again M we already know. So just substitute the values and after substituting, you see first step we are multiplying these two matrices and we are having this answer, right? And again further simplification, we are ending up with the matrix like this, right? So now we are introducing this that is divided by 18 inside this matrix. So minus 18 by 18 gives you minus 1, right? So likewise, you see here we are having a matrix like this. If a matrix has elements arranged in this way, and this is known as Jordan block, right? The next step is calculating B cap. It is nothing but M inverse of B. So again when you substitute, we are ending up with matrix like this. And the next thing is C cap. It is given by CM. We know what is C and this is your value of M. So just when you multiply here, we are ending up with the C cap matrix like this, right? The next thing is the Jordan canonical form of state model is, this is given by this basic expression, right? Differentiation of z, okay? Z dot is jz plus b cap u plus and y is c cap z plus du. And here this z is nothing but z1 dot, z2 dot and z3 dot here. We know what is meant by j, right? And here it is, this z is z1, z2, z3 plus we know b cap value which gets multiplied with u and again y is given by C cap into Z, right? So C cap is given by 441 into Z1, Z2, Z3 and here the value of du is not defined, so no need to include this term, right? So finally we are ending up with this form of matrix, right? So from these matrices we have to tell whether the state equation is controllable and observable. So you see it is observed that the elements of the rows of B cap are not all zeros, right? You see B cap, okay? This is your B cap and this B cap elements, there are no zeros. Therefore, the system is said to be controllable, right? And again, the columns of C cap are not all zeros. Therefore, the system is said to be observable, right? So, whenever the question is asked without mentioning Kalman's test or Gilbert's test, you can proceed with the Kalman's test because it is quite simple. If it is asked specifically, then you have to do accordingly, right? So here comes the end of this problem. If you have any doubt, let me know in the comment section. Thank you.